Okay, so today we're going to look at buffer solutions, and in particular using a strong base to make that buffer solution. To work out the pH of such solutions, we need to use two equations. The first equation is using the formula pH equals minus log H plus ions. The second equation is where you use the formula the concentration of H plus ions equals Ka multiplied by Ha divided by A minus. Now, these two terms, concentration of HA and concentration of A minus, are derived from the concentration of HA after the addition of the base. So this is the concentration of the acid, or it's the concentration of the acid in excess, and the concentration of A minus is normally the concentration of the base. Okay, so from these two bits of information, we need to therefore work out the concentration of HA at the equilibrium or after the addition of the base. We need to work out also the concentration at the end. So during the reaction, we're going to add two liquids together, or two solutions together, and at the end we also need to know the volume at the end as well. So here are the following steps I would recommend you take in working out the pH of such a solution. So the first thing you need to be able to do is to work out the number of moles of HA at the beginning of the reaction. Number two, you need to be able to calculate the number of moles of the base. Number three, you need to work out the total volume. Number four, you now need to work out the new concentration of both HA and also the base. So then we're looking here really for the number of, not just the number of moles, but the concentration of the HA, which is in excess. And also 5 would be the concentration of the A minus after addition. From this, you should now be able to work out, so from these bits of information, you should then be able to work out initially the concentration of H plus, and then after that you can then link that back to working out the pH of the solution. So to exemplify this, we're now going to have a look at an examination question. So if I scroll downwards, here it is. So this is from a Chem Unit 4 paper. So in this question paper, it says to us that we're using an acidic buffer, and we need to work out the pH. It says calculate the pH of this buffer solution when we're going to use a concentration of 0.125 mole per decimeter cubed of the sodium hydroxide. We're using a 10 centimeters cubed of it, and of the weak acid HX, we're going to have a 0.174 mole per decimeter cube solution, and we have 15 centimeters cubes of that as well. Finally, we're told that the Ka for the weak acid is 3.01 times 10 to the minus 5. So let's put these things together now to work out our pH value. So first of all, let's go back up again and have a look what we have to do first. So first, we need to work out the number of moles of HA. So in our case, we haven't got HA, we've got HX, but the same kind of idea. The number of moles now of our acid, HX, is going to equal the concentration times by the volume divided by 1,000. So it's going to be 0.174 multiplied by 15, and that's all divided by 1,000. So if I take up my calculator, and that equals 0.00261 moles. Okay, so that's our first thing done. Next thing we need to do, if I scroll back up, is to work out the number of moles of the base. Okay, so the number of moles of sodium hydroxide is going to be equal to, now, so we're looking at this value of the concentration, and that's our volume. It's going to be 0.125 times by 10 divided by 1,000. And that equals 0.00125. So now we have the number of moles of the weak acid, which is 0.0261 moles. We also know the number of moles of the sodium hydroxide. We can work out how much is going to be of the weak acid is going to be left over once these two things react. So we're going to just do a very simple calculation. So the number of moles of HX in excess equals 0.00261 take away 0.00125, and that equals now 0.00136 moles. Okay, so we've worked out the number of moles of HX in excess. We also know the number of moles of NaOH as well. So we can now work out the next stage, which is the concentrations of HA and the concentration of A minus. Now, to be able to do that, we need to then re-emphasize the total volume that we have now. So we've got this value here, 10 centimeters cubed, and we've also got 15 centimeters cubed as well. So the total volume now, is going to be equal to 10 plus 15, which is 25 centimeters cubed. Okay, so we're now going to work out the concentration of HX and also of the A minus. So the concentration of HX and excess obviously is going to be equal to 0.00136 times by 1000 divided by 25, and that value comes to, so obviously now we're looking at concentrations, so it's going to be 0.0544 moles per decimeters cubed. So this is the concentration now of HX in the solution. Okay, the next thing we have to work out is the concentration of A minus. So concentration of A minus will equal the number of moles of it that we have, which is 0.00125, times by 1000 divided by the new volume, which is 25. And that works out to be 0.05 mole per decimeters cubed. Okay, so we now have HX and A minus, so we can now plug in to work out the concentration of H plus. Concentration of H plus equals Ka times by the concentration of the weak acid at the equilibrium multiplied by the concentration of our A minus. So we now look at this, and let's scroll up a little bit further. That equals this value here, which I was given in my equation, so 3.01 times 10 to the minus 5, multiplied by the concentration of the acid, which is now 0.0544, divided by the concentration of A minus, which is 0.05. We get 3.27 times 10 to the minus 5. Okay, so the final step now is to work out the pH, and pH equals minus log the concentration of H plus, which is that's why it's worked out now. And remember that you should also, I don't know, I've missed this out, you should have also worked out the units for the concentration of H plus, which is moles per decimeters cubed. So we're now going to put the numbers in, minus log, and we've got 3.27 times 10 to the minus 5. You should always keep the numbers in the calculator, and that will give you a value of pH of 4.49. And remember, the question does ask for you this here to give you a value in 2 decimal places. Okay, so that gives us now a value of 4.49 as the correct answer. Now, before I finish, I need to quickly show you where some students make some mistakes. Okay, so one of the key mistakes is they don't use this equation here. Okay, what they use is the equation where they take the concentration of H plus using the formula Ka equals H plus squared divided by the concentration of HA, and that's not the way you should be doing this. It's not the same kind of question. We're looking at buffer solutions. We're not looking at just simply weak acids here. We've got a weak acid, and we've also got now its conjugate base as well, the salt in there as well. So that's where you need to really keep an eye on it so you don't make a mistake there. So in terms of marks, I would give a mark for the working out the moles of both of these two. I'd also work out the mole and give me the final concentrations of HX and A minus. That would be a mark for me as well each. 1 mark for working out the concentration of H plus, and then finally 1 mark for working out the pH of the buffer solution.